Hey everyone, welcome to the next video. As you can see from the title, we're going to be discussing center of mass in this video. Now, I was really racking my brain trying to think of a way to sort of motivate this discussion here. And the idea that I had was, well, let's watch a video of some people throwing axes around, right? So let's do that. Okay, so the reason that I'm showing you this, right, is you might be wondering as you watch these axes fly through the air, right? How could we use physics to kind of predict the motion of the axe? Because it obviously isn't a point mass, right? And up till this point, we've been just thinking about point masses, right? Sorry, I'm mesmerized by these axes. And so anyway, let me just gather my thoughts here. The idea is, right, that there is a specific point on these axes called the center of mass that actually behaves like the point masses that we're used to dealing with, right? And so if we can kind of determine where this point lies on a given object, then we're going to greatly enhance our ability to analyze the motion of all kinds of different objects. And so that's why this is useful. And so I think that's probably enough of watching these people throw axes, but oh yeah, this guy's a weeb 100%. I probably shouldn't have said that. Anyway, okay, let's stop the video here and actually get to work. Okay, so the motivation here, and let me just summarize what I was sort of incoherently rambling about there in the document. So axe throwing, right? So how could we predict the motion of something complicated like a thrown axe? And the idea is that we simply focus on the axe's center of mass. Okay, and this obviously applies to, you know, all kinds of objects, not just axes, but I thought that that might be, like, I don't know, a cool example to look at. So what I want to do is show you how you would calculate the center of mass in one dimension, right? So I'm going to say, consider a collection of n point masses, right? This just means we have some number of point masses. And they're all lying on the x-axis. Okay, so the center of mass, and I will denote this by, or I should say with, I suppose. No, I think it's by a capital X. Okay, I think this is a pretty common notation. You might see other things. You might see like X bar or X with CM in the subscript. They all mean the same thing, right? But I will use a capital X, which I think is a pretty standard notation. So the center of mass of this collection of point masses is given by, and the definition is this, right? So in the numerator here, we write m1 times its exposition plus m2 times its exposition plus ... right, all the way down to the very last one, which will be m sub n with exposition x sub n. And in the denominator here, we have simply the sum of all the masses, right? And maybe you can already see, I'm going to talk about this, of course, because I can't not, but you can already maybe see that the dimensions of this are going to work out to be position, or I should say, this is a position, but the dimensions will work out to be a length as we would expect, right? And I'll just show you a few different ways of writing this. So if we define, I think this is another common bit of notation, capital M to be the sum of all the masses, right? List all the way down to the nth mass. Then, and I'm just going to copy and paste this in the interest of saving a little bit of time. I promised you this would be a short video, and I'm going to do my best to honor that promise. So it's like, it looks like this now. And there is one final way we could write this, and that would be using the sigma notation that perhaps you've seen before, say in a math class. It's okay if you haven't, right? It's not super necessary, but I'm just going to put this here because this is the other way you might see this written, say if you look in the textbook or at some online resource, right? But these all say the same exact thing. And I promised you I would check the dimensions. And, you know, I think we all know, right, that it's going to work out to be dimensions of length, but we're going to do it. So square bracket x, and this is just going to be, right, a mass times a position over a mass. The masses cancel, and so this works out to just have dimensions of length, as we already have mentioned. And of course, the corresponding SI unit here is the meter, right? So there's a few things I want to say about this before we talk about the three-dimensional case and look at some examples. So what I want to say is that the center of mass of a collection of two masses will lie on the line connecting the two masses. And this is more something that's important to mention actually about like the two-dimensional or three-dimensional case, because I think that maybe we can all see from this definition that of course this is going to lie on the x-axis, and it doesn't even have to be just two masses, it could be more masses, right? And so this certainly holds true for the one-dimensional case, but we'll see that it also holds true for the two-dimensional case. And if you really want to, you could show for yourself that it works for the three-dimensional case. Yeah. Okay, so let's generalize this to the three-dimensional case. And so we first need to define our notation, right? So I'm going to say, generalizing this to the 3D case. And, you know, we're not really going to work with 3D systems here. I will give you, you know, at least like one or two homework problems on this, but they'll be two-dimensional, right? Because that's all we really have need for. But anyway, we can define, and I'm going to write now capital R, and this is a vector, and it's given by the ordered triple where x is, or big X is in the first position, big Y is in the second position, and big Z is in the third position here, right? And let me actually just fill this in right here. And the way I'm going to write this is perfectly analogous to the one-dimensional case, but this now is a position vector, right? A three-dimensional position vector, as is this R2, and then we take this all the way down to M sub n, R sub n. And then down here we still have the sum of the masses, right? Cool. And I mean, and that's it, right? That's all that we have to do to get the three-dimensional case. We just change the positions, the one-dimensional positions, to three-dimensional position vectors, and we're set. So hopefully that's not tricky or confusing. And if it is, I think that hopefully after we work this example and you try it for yourself, it will become clearer. Okay, so what I want to do is look at an example, and I'm going to bring the whiteboard over here so I can make a sketch. Okay, so the example is we want to compute the center of mass of a point like mass m1 equals 2 kilograms at r1 with x position 2 meters and y position 3 meters, and another point like mass with mass 1 kilogram at the position vector -1 meter, -4 meters. So we'll make a quick sketch. I'm going to draw my x and y axes. And then I'm going to make some tick marks here to kind of try to hopefully make this somewhat accurate. And so our first mass is in the first quadrant, right? And it might look something like this in our sketch. I'm going to say M1, and we can call this position X1, Y1, right? Now, for the other mass, that's going to lie in the third quadrant. And let's try to also make this reasonably accurate. So it looks like it should be maybe about here. And this is M2, and we can write this ordered pair as X2, Y2. And just for later purposes, I'm going to draw the line that connects them just as a dotted line. I'm going to do my best to make this a straight line here. Okay, cool. So let's actually calculate this. And we're going to go about this much as we would for a calculation that involves any kind of a vector, right? And we're going to do it component by component. So let's solve first for the x component of the center of mass. And we'll find that x equals, and I'm actually going to copy and paste this from my notes, but I'll talk about it as I do it. But let me write it out symbolically first, and then I'll start doing that. So it's just m1 x1 plus m2 x2 over m1 plus m2, right? And plugging the numbers in, I think that the numbers are useful here because we want to look at the position of our center of mass vector and confirm that it lies on the line connecting the two masses, right? So plugging the numbers in, this is what you get. 2 kilograms times 2 meters plus 1 kilogram times -1 meter, all over 2 kilograms plus 1 kilogram. And this works out to be very nicely, hang on, this is actually, yeah, it's 3 over 3, right? So it just works out to be 1 meter. So that's a nice result. Then we do the y component, right? And this is going to look very similar. In fact, it's going to look so much similar that I am going to just copy and paste this and change everything as appropriate. So now we're talking about y. So big Y. All the x's become y's. Everything else stays the same. And so we just have to adjust these position values here. So this becomes 3 meters, right? Because that is the y position of the first mass. And this becomes -4 meters here. -4, okay. And we should find, let me see here, this should work out to be just 2/3. And so we say thus r, and remember this is a vector. This is just the vector that takes us from the origin to the position of the center of mass. And symbolically it's just big X, big Y, and numerically it is 1 meter and 2/3 of a meter. Cool, and we'll just try to draw this in really quickly on the sketch and make sure that it sort of looks correct. So 1 meter up 2/3 of a meter, and there you go. Right, not bad. One thing to note is that this, and I'll actually write this as an X maybe, that's what I usually do, is this is closer to the larger mass, right? And that is just a consequence of our definition here. And that will always be the case for a collection of just two masses. And so that's another little sanity check you can perform, right? If you have a two-mass system and you want to calculate the center of mass, you should find that it is closer to the larger mass, right? Okay. So that's that. We're going to talk about some of the implications of this definition, right? So let me just bring this to the maximized position. And so for this, we're going to focus on the one-dimensional case again, and everything that we find here will carry over to the three-dimensional case. So let's say let's focus on the 1D case again. And for definiteness, we'll consider the x, let's just say x-axis. So now it's like once more we're thinking about a collection of point masses that are all lying on the x-axis. So what I want to do is just basically copy and paste the definition that I had from before. This is exactly the same thing we wrote, nothing changed, right? And what I want to do is kind of imagine, right, that each of these masses has no net force on it. And you'll see why I am saying this in just a few minutes here. So let's say if each of the individual masses has zero net force acting on it, and we take the second derivative of both sides of the above equation with respect to time, we find, and so let's do that. I'm again going to copy and paste this, and then I'm just going to put the dots over, the dot notation, remember, right, for time derivatives. So let's get some double dots over this. Then over this, over this thing, and then finally over this one. And actually what I want to do is rewrite the left-hand side here more suggestively, and let's write it as a capital A sub x, and this is hopefully, or maybe you can see that this is now an acceleration, right, because the second derivative of position is an acceleration. The second derivative of position with respect to time is an acceleration, and we'll just use a capital A to indicate that it's the acceleration of the center of mass now that we're talking about. And so what we have, right, well, if this is just the first mass times its x acceleration, and this is just the second mass times its acceleration, and this is just the nth mass times its acceleration in the x direction, we can rewrite this as maybe something like this: the net force on mass 1 in the x direction plus the net force on mass 2 in the x direction, right, all the way down to the net force on the nth mass in the x direction, and nothing changes about the denominator. We still have just the sum of all the masses. But by hypothesis, right, we said that each of the individual masses has zero net force acting on it. So what we find is 0 plus 0 plus ... plus 0. So just a bunch of zeros being added together in the numerator And then, well, let me actually just write big M here because I haven't really been using that notation. Just the sum of the masses in the denominator, and this, of course, is 0, right? So what this means is that we see that the center of mass must move with constant velocity, which might be 0, right? Because 0 is still constant. And maybe you can imagine a case where you have two masses, right? One-dimensional case where you have two masses of the same mass, and they have the same speed, but they're moving away from each other, right? And I think in that case, it's not too difficult to show that the center of mass stays in one fixed location, right? And that just comes back to what we said, where it's moving with constant velocity because it's not moving at all, right? And 0 is a constant, okay? Cool. So I guess, before I move on, what I want to do is just stress to you that a lot of times we don't actually even have to do like a complicated calculation to determine the center of mass of, say, a system of point masses or even a three-dimensional object, right? So let's get the whiteboard back up, and I'm just going to make some sketches here of like maybe one or two objects and just show you that you kind of already have a sense of what this looks like. So the first thing that I want to consider is maybe a rod, a uniform rod. So this looks like a cylinder, right? That's oriented, say, along the x-axis. And if this has length L, what we're saying is, right, like this is x equals 0, and this is x equals L. Well, the center of mass of this thing is just going to be at the geometric center, right? And so it would be like right here, right? And, if you've ever tried to, say, balance like a pencil on your finger or something like that, then you already have like an intuitive sense of this, because if you can position the pencil so that its center of mass is directly over your finger, let's say like if this is your finger and it's pointing out of the screen, right? So if you can position the center of mass of the pencil directly over your finger, and if you could hold your finger perfectly still, you would find that this thing balances, right? It doesn't, fall over. And that has to do with like torque and stuff. We'll talk about that a little bit later on, not in this video, but in another one. But I think that you probably have like, at least some kind of intuitive idea about this stuff. We could look at maybe one more example would be like a cube. And this is a three-dimensional example. Obviously, I'm going to do my best to sketch this. I don't know how it's going to turn out, but let's see. So I have my three-dimensional Cartesian axes now, so x, y, and z, and I'm going to try to sketch a cube. This is going to be tough. Let me see here. So I probably want to start out with, oops. Let's start out with drawing the top. So this actually didn't turn out so well, but the idea is that for a cube, right? Maybe I can find something on the interweb. Hang on, let me just see really quickly if I can find something better than my awful drawing. Center of mass of a cube. Okay, here's one that I like. It's like the first one that popped up, right? And so we see that the center of mass of a cube, actually I like this one. Let me make this bigger. No, let's come back to this one since... Okay. So this is here. He's got a few. Actually, I know this guy. He does really good educational stuff. Anyway, this sketch here is much better than mine, of course. And you know what it's sort of trying to show is that the center of mass of the cube is just at its geometric center, right? And so if it's a cube of, you know, length, width, and height a, then this is just going to be like x position a over 2, y position a over 2, z position a over 2, right? If you say you define your origin to be at like one corner of the cube, right? And this is not super important because, as I said, we won't really be dealing with many three-dimensional objects, but I just want to stress to you that you probably already have a pretty good idea of what the center of mass is of many symmetric objects, right? And so don't, you know, forget things that you already kind of know when you get deep into doing calculations, because it's easy to do, and we hate to see that. Okay. So let me bring the document back up. Okay. And there are different types of distributions of mass, right? Well, there's two that we want to discuss here. And the words that we use for those are continuous and discrete. So I don't have very much to say about this, but just so you're clear on the terminology, when I say something like continuous or discrete, I'm going to say that a discrete distribution of masses is simply a collection of masses that we can accurately treat as point masses, right? And so you could think maybe of like some marbles on the floor, right? Marbles are spherical, so they're very symmetric, and we can definitely say that the center of mass of a marble is basically at its geometric center, right? So this is something that is an example of maybe things that we could treat as point masses and a discrete distribution of mass. And so a continuous distribution of mass is a solid object that can't be accurately modeled as a point mass. And this would be like an axe, right? We can't, you know, I mean, we can think of it as like, you know, just a big collection of atoms, I suppose, but that's not particularly useful, right? And so it's good to categorize the mass distribution that you have before you attempt to do any calculations, because in general, discrete mass distributions will be calculable, if that is in fact a word, right? But calculable via, like, you know, this kind of a formula, or more precisely this kind of a formula, right? Whereas for a continuous distribution of mass, you'll have to do an integral probably, unless you can just look at it and argue that you know where the center of mass is by symmetry. And I'll show you an example towards the end of the video here of doing an integral to calculate the center of mass, even though it's not something we'll actually really do. Okay. So there is, okay, so we've talked about the difference between a continuous mass distribution and a discrete mass distribution. So let's talk about this idea of mass density. This will be the last thing that we need to hit, I think, before we can wrap up here. So let's define first a linear mass density, right? So the linear mass density of an object can be written, and we'll call it lambda, not capital lambda though. And this is just defined to be a mass over a length. And the picture that you want to have in your mind here is of the rod that we were looking at previously, right? Especially if it has, say, like if it's cylindrically shaped and it has a very small radius compared to its length. And we can rearrange this, right, into perhaps a more useful form and say that the mass is given by the linear mass density times the length. We'll say then, likewise, the areal, I don't know if that's actually a word, but it's not drawing the red line under it, so maybe it is. The areal mass density of an object can be written, you probably see where I'm going with this, but I'm going to call this sigma, and this is just defined to be a mass over an area. And then finally, the volumetric mass density of an object is, we'll call this rho, and this will be a mass over a volume. And so this definition can be useful, right? And this definition can definitely be useful. This one not so much, because it's not very often the case that we have something that we can just model as like two-dimensional, like as just having an area but no volume, right? You could think of maybe a piece of paper, because it has, say, dimensions of length and width, let's say, that are very large compared to its thickness. And so maybe that would be the useful thing to keep in mind here. And for volumetric mass density, there's any number of things we could come up with, but probably the nicest is a sphere, right? Okay. Cool, so then I just want to show you what the definition of the center of mass looks like in the continuous case. So we can adapt our definition from the discrete case. Let me say our definition for the center of mass from the discrete case to the continuous case by writing, and this will just be one-dimensional because these for like 3D situations can just look disgusting, and we will not be doing anything like that. And so what I want to write is, it's 1 over the mass, the total mass. Let's say we're talking about one object here. It's the total mass of the object, well, 1 over the total mass of the object, and then we integrate, right, from 0 to the total mass of the object, let's say in the x direction, just to be definite, with respect to, the mass. So we have like a differential that depends on the mass, and we'll see how to deal with this in this example that I'm about to do. So this is more just for your general information. Don't worry so much about this if it doesn't make sense, but I think it's something that I should show you. Okay, so in this example, we want to calculate the center of mass of a uniform rod with mass m and length L. Well, we already know the answer, right? We were just talking about this, and we know that if we define our x equals 0 to be at one end of the rod, say the left end, and x equals L to be at the other end of the rod, we know that this is just going to occur at L over 2. But let's show that, right? So what we want to do is, considering our definition of linear mass density, and when I say uniform rod, this just means that it has a constant linear mass density, right? So the linear mass density in this case is just a number, and remember we call that lambda, right? So we have from the definition of linear mass density, right, that the mass is lambda L, right? And from this we see, right, we just take a differential on both sides, that dm is lambda dl. And L is just a dummy variable, right? It just indicates the length, so we could call this x if we want to, and that's what I'll do. I'll say lambda dx. Cool, so now it looks like we have something we can integrate. And we just have to fix our limits of integration, right? Because in the formula that I just wrote, the limits are m equals 0 and m equals big M, right? So we just need to just change those to something geometric. And the way that we do this is we note that, let's say then, noting that at x equals 0, we have 0 mass, and at x equals L, we've encompassed the full mass of the rod. We change our upper limit of integration to L, the length of the rod, right? Then, and so you're gonna have to be careful. Well, I should be more careful, but you're gonna have to be careful when you interpret what I'm writing here, right? And technically, I probably should keep this. I should write this more like maybe script M or something, just to show that it's not. It's just bad mathematical form to write it the way that I had it, right? But for our purposes, it doesn't really make a huge difference. But what we have then is, and it doesn't end up mattering because we're going to integrate with respect to x anyway, is that our integral becomes this, 1 over the mass of the rod times the definite integral from 0 to L, and then lambda dx. And lambda is a constant, of course, right? So we can just pull that out front. And then we just have the integral of 1, right? From 0 to L. I'll just write dx here. And then this becomes lambda over m something's not working here. God, and I'm so close to the end of the video, I really don't want to have to re-record this, so just bear with me while I figure this out. Over m, integral from 0 to L, lambda dx. Pull that out front. It's looking like this is okay, but I know we're not going to get what we're supposed to get here. Because what we find is like this is going to just be L when we evaluate the integral, and let's see here, lambda, right, is just m over L. So it looks like we'd find that the center of mass is at 1. It doesn't really make any sense. Oh God, what is wrong with this? Oh, I forgot my x. Okay, that's obviously the problem here. Okay, so let me do this again then. Okay, cool. I'm glad that I at least figured it out. I apologize for making you wait. So remember that there's an x here, right? It's x dm. And so what we have to do is we just rewrite this. And now this is lambda x dx, right? And we can still pull the lambda out in front. And then now we're integrating from 0 to L x dx. And so we have lambda over m. The integral, the indefinite integral of x with respect to x is just x squared over 2, right? So x squared over 2, and then we change, or we put in our limits of integration, so we're going from 0 to L. Okay, we're almost there. And what we find is lambda over m times L squared over 2. And then remember that lambda is m over L. We divide that by m and multiply by still L squared over 2. I'm going to be very careful here because I'm scared now that I've made another mistake or something, but I think we're looking good. And so this works out to be 1 over L times L squared over 2, and we're good because we find, after canceling a factor of L, that this is just L over 2. Okay, cool. So we found what we suspected, right? Which is that it should just occur, the center of mass, that is, should just occur at the geometric center of the rod. So that's good, right? Yeah, we struggled a little bit. Well, I struggled a little bit, I guess, but we got there. Okay, cool. That's it for this video. Of course, if there are any questions or anything like that, feel free to hit me up. I will do my best to help you, and I will see you in the next video.